Swayam Prabha. Digital India. Educated India.
I welcome you all in this course on refrigeration and air conditioning. Today we will discuss the infiltration. This infiltration is the infiltration in a building. In this lecture I will be covering, first of all, introduce you what is infiltration, then driving mechanism of infiltration, how the infiltration takes place, air exchange rate, and estimate method of infiltration. There are two methods, crack length method and air changes method. So, we will start with the introduction of infiltration. In any confined space, for the purpose of air conditioning, the air enters in the form of supply air, which includes ventilation. This is desired entry of air in the room. I mean, ventilation is desired, and there is infiltration also from different, because a room is not a leak proof entity. No building is a leak proof entity. So, there is always chances of entering outside air entering into the building, and this is known as infiltration. And sometimes the air leaves the room. It depends upon the outside atmospheric conditions and inside atmospheric conditions. When air comes out of the room, that is also not desired movement of the air, and this is known as exfiltration. So, there are two things, infiltration and exfiltration. Normally, infiltration in the confined space takes place. Ventilation in the room is essential. Without a ventilation, the air conditioning system will fail. It will become simply a cooling system, because through ventilation fresh air enters into the system, and this fresh air maintains the quality of air in the room, or quality of air which is being circulated in the building. If we reduce this amount of fresh air, this ventilation air, then definitely the load on the cooling coil will reduce, because outside air, which is fresh air, is in summer, let us say it is available at 40 to 45 degrees centigrade. Instead of using this air, if I use return air which is coming from the room, it is at 27 degrees centigrade. So, definitely if I do 100% recirculation, 100% recirculation of air, the load of the air conditioning coil or system will be less, but at the same time I will be losing the quality of air inside the room. And quality of air, the main problem will come with the scarcity of oxygen and excess of carbon dioxide. Both have very harmful effect on the human health. Normally it is witnessed, especially where the population density is high, like schools or theatres, though the temperature and humidity is maintained, but the level of carbon dioxide is very high. Normally it is recommended that carbon dioxide should be around 400 ppm, and level of carbon dioxide in the occupancy should not be more than 300 of this, maybe it can go up to 700 ppm, but not in any case more than 1000 ppm, and that is alarming situation. When it exceeds 1000 ppm, then its effect on the health are visible. People have headache. First of all, headache starts. You will find many people who are sitting in AC environment, they have headache due to this excess of carbon dioxide, the feeling of nausea, cramps, pain in the legs, that is due to the excess of carbon dioxide. And it has witnessed that in many of the places like schools or computer labs, the level of the carbon dioxide is up to 2400 ppm. That is very alarming. So, that is why ventilation in any building is very important. Now, let us talk about infiltration. Regarding infiltration, it is undesired flow of air in the building, and because as without temperature difference, bulk of the heat cannot move, the heat cannot transfer without temperature difference. Similarly, bulk of the fluid cannot be transferred without pressure difference. So, there has to be pressure difference, inside pressure and outside pressure. There has to be some pressure difference which will act as a driving force for the movement of air inside the building or take away air from the building to the surroundings. Now, how this pressure difference is generated? That is one issue. And how we can prevent the infiltration of this air into the building, because infiltration brings the load on the cooling coil also. For example, inside the room, suppose the coil room temperature is maintained, let us say 24 degrees centigrade, and outside air is 42 degrees centigrade. This is 24, 50%, and this have some humidity, let us say 60%. Let me take psychometric chart. Now, here suppose this is inside condition, not the air supply condition, this is inside condition, and outside air is available, let us say 40 degrees centigrade and 50% relative, or let us say this one, no, this one 50%, 50% relative humidity. This is outside air. Now, air available here enters the room. It enters the room, and after entering the room, this air will bring energy to the room, and this energy, suppose this is the final state, this is the supply state. Now, we will draw a horizontal and vertical line, and we will get a state A. This will be in the form of sensible heat and latent heat. So, air which is coming into the room shall bring energy in the form of sensible heat, and this is latent heat, and this is sensible heat addition by the air. Now, if I calculate these values now from here, then this enthalpy of the air which is at 40 degrees centigrade temperature and 50% relative humidity is approximately 110 kilojoules per kg, and at this point the enthalpy is 48 kilojoules per kg. So, this is the difference, 110 and 48, it is going to be 62 kilojoules per kg. This much of energy will be entering the system. Suppose infiltration rate is 1 kg per second. So, 62 kilowatts is quite high. 62 kilowatt is tens of tons, and from this we can also find what is the sensible heat addition, what is the latent heat addition. So, sensible heat addition, if we are able to find the enthalpy at A, and that is 60, 70, 80, sorry 60, 62, 64, 65, approximately 65 kilojoules per kg. Now, these informations are helpful when we do load calculation in the system, because when we design an air conditioner for a building or a house, in that case infiltration is also taken into account, and this infiltration is the load due to this infiltration is also added in the total load of the building. Now, the problem is how to estimate the infiltration in the building. Now, before we do the estimation of infiltration in the building, let us understand the driving mechanism of infiltration in the building. Now, let us talk about a high-rise building of 5 stories or 10 stories, or maybe low-rising building also. It is not totally airtight. It has certain height, and for example, in case, let us take example of winters. So, in winters, inside temperature is, we are maintaining inside temperature 24 degrees centigrade, right. Outside temperature is, let us say, 5 degrees centigrade. Now, what is going to happen in this case? In this case, at the bottom of the building, outside temperature will be greater, outside pressure will be greater than inside pressure. This building will behave like a chimney. You must have studied the movement of the fluid in the chimney. Same way, the movement of the fluid will take place here. Here, outside pressure is greater than this pressure, inside pressure. So, air will move in from the bottom. And this you must have realized also during the winters, there is a lot of infiltration in your house from the bottom of the door or from the bottom of the windows. This is due to this pressure difference only. And the pressure, when we are going up, the pressure in the building will reduce, pressure outside will also reduce, since the density of air is higher in this case, because density is P V is equal to mRT. So, density is P over RT. So, density of the air is equal to pressure divided by R temperature. So, the moment the temperature is reduced, the density will increase. So, definitely at lower temperature fluids have higher density. So, density is high, that is why the fall in the pressure of air, because when we are moving up, the pressure will reduce. Here also the pressure will reduce, but the fall in this case, the fall in the pressure will be larger, and it is possible that this fall in pressure is such that, and it always happens, not possible, it always happens, then here the pressure, outside pressure, this is P2, let us say this is P1. So, here at the exit P1 is greater than P2, and here P1 is less than P2. If I draw a diagram between the fall in pressure with height of the building, it is going to be like this. This is pressure and this is height, or it is denoted by H in the buildings. Now, in the case of outside pressure, it is going to be like this. This is outside pressure, and this is building pressure, pressure of the building inside, and this is pressure outside. And this is the fall in the pressure with height of the building, and we get a place or a point where both sides the pressure is same. This is known as NPL, neutral pressure level. At this point, there will not be any movement of the fluid. Otherwise, from the bottom, in the winters, from the bottom, air will enter the building and it will leave from the top. In summer, definitely the scene is going to be different. In summer, the air will enter, because outside temperature is higher than inside. Inside temperature, let us say 24 degrees centigrade, outside temperature may be 45 degrees centigrade. So, situation will reverse. Air will enter from the top and leave from the bottom, infiltration air. This property was also used, this movement of the fluid was also used for the cooling of the building. You must have observed in the old buildings there were ventilators, and the function of ventilators was just to ensure the movement of air from top to bottom position in the summer season, right, so that proper ventilation in the building is maintained. Now we are talking about the infiltration. Suppose because air is not calm, air is also moving with certain velocity. Suppose on the building air moves across the building, building acts as a bluff body. Building acts as a bluff body, but definitely at all the points there is going to be a positive pressure. So this is building on the both sides. If I show the pressure of air, it is going to be wind side and leeward side, this is negative pressure, and air will be flowing out of the building right from the top to bottom. So air movement in infiltration is also important. We cannot always say that the movement of the air will be like this. Suppose the wind velocity is high, then air will enter from all the possible points in the building. Now after this, we will take up how to quantify the infiltration. How to calculate the amount of air which is getting into the building. Before that, I would like to explain air exchange rate. Air exchange rate. Say in air conditioning, we never say that the flow of air in the building is 5 meter cube per hour or 8 meter cube per hour, 8 meter cube per hour or 5 meter cube per hour, or let us say 1000, 10,000 CFM. It is always expressed in terms of CFM or 20,000 of CFM. The issue is this is only flow rate. It depends what is the size of the building. In a building, 1000 CFM may be very high in a small house. In a small house of 2 rooms, suppose there is a 2-room set. In a 2-room set, 1000 CFM may be very high. But in a multi-story building of 3 story or 4 stories, this may be negligible. That is why air movement in the building is always normalized with the volume of the building or the volume of the occupancy, and that is known as air change rate. It is equal to volumetric flow in the room, volumetric flow in the air of air in the room divided by volume of the room. It means the movement of air in the room in the unit of volume of the room. If I say air change rate is 1, air change rate is 1 means in 1 hour time, it is volumetric per hour. So volume of the flow of air in the room per hour divided by the volume of the room. That means suppose volume of the room is volume of the building is 100 meter cube, right, and the air flow in the building is 500 meter cube per hour. We will say that the air flow in the building is 5 air changes per hour. So it is expressed in terms of air change rate per hour, ACH, and 5 ACH means per hour the flow of the air in the room is 5 times the volume of the room or volume of the building. Normally for air conditioning purpose, it is a thumb rule that normally 5 to 7 air changes per hour are maintained in a building. If it is evaporative cooling like desert cooler is used, we can go up to 12 or 15 air changes per hour, but 12 and 15 air changes per hour is a very high flow of rate in occupancy. So after air changes per hour or air exchange rate, we will go for estimate method for infiltration. So there are 2 methods, one is crack length method, other is air change method. Crack length method is more scientific, I mean some calculations have to be made in this crack length method, but air changes method is very practical. Normally it is used by the practicing engineers. For the air tightness of the building, now we have to quantify the air tightness of the building because no building is absolutely airtight. We can always say that it is, I mean it is very good, air tightness is very good, or it is fair, or it is poor, or it is excellent. A blower door test is done on the building. In a blower door test, there is a air tightness test of the building. On a door, a blower is fixed, all the windows and doors of the buildings are closed, a blower is fixed, and certain amount of pressure is maintained in the building, right? And when this certain amount of pressure is maintained in the building, it is noted what is the flow rate of this blower in order to maintain that pressure, and we will get 1 point. And now we will keep on changing the pressure above the atmospheric pressure, and we will be getting different points for different pressures. When the pressure is high, flow rate will be high. When the pressure is low, definitely flow rate will be low. And variation of pressure, I will tell you the range. It is between 4 Pascal to, let us say, 25 or 30 Pascal. 4 Pascal, 25, 30 Pascal, and we get a curve like this. Similarly, we start creating vacuum in the building also, and we get another curve. So, here let us say this is 0 pressure and 0 flow, and this is positive pressure, positive flow Q, and this is positive pressure, this is negative pressure, and this is suction from the building. Now, this curve has relationship as delta P is equal to some constant, Q is equal to some constant delta P raised to power n. So, for a particular pressure difference, the pressure difference we can always measure, inside and outside pressure difference we can always measure, we can find how much air is flowing into the building. Now, this value of infiltration in the building is divided by the exposed area of the building, and we get a certain value, and this value is used, this value is used for, this is generalized value, and this value is used for calculating the infiltration in the building. I will give you an example of residential building where air leakage area has to be calculated, Now, air leakage area is exposed area into unit leakage area. This method is used for residential building only, it is not for commercial building. So, unit leakage area we get from a chart. We get from a chart where it says that the tight building is, we say tight building where unit area is 0.7 centimeter square by meter square, and it is a good, then it is 1.4 centimeter square by meter square, and this average 2.8, leaky 5.6, very leaky 10.4, and so on. Now, this unit leakage area is multiplied by this exposed area of the building. Now, exposed area of the building is the area of the wall. I am showing you the plan of the building, area of the wall plus area of the roof excluding area reserved for the garage. So, this is exposed area of the building, and then we get a leakage area, and this leakage area is multiplied by infiltration driving force IDF, and we get total infiltration in the building. Now, for calculating IDF in a residential building for the cooling purpose, it is going to be equal to 25 plus 2.5 module of delta T, 0.38 plus 0.12 AL flue divided by AL divided by 1000. Now, delta T is the temperature difference, inside outside temperature difference. AL flue, leakage area flue, if there is a shaft, normally in our country we do not have lifts or such an opening in the houses. So, this can be neglected and we can take up to here, and this will give us the infiltration driving force, estimate of infiltration driving force. And if the provisions of flue or fireplaces is there, then we can take AL flue also, and this infiltration driving force, when it is multiplied by the leakage area, that will give infiltration in the house, but this is strictly for residential buildings. Now air change method. Now air change method, it is normally it is very popular with the practicing engineers. In air change method, quality of construction is estimated, tight, average or loose, that is it. It has three classifications, and the equation for number of changes, number of air changes per hour is equal to, let us compare with the tight with the loose. Suppose the building is tight construction, then A is equal to 0.15 plus B is equal to 0.01 multiplied by the velocity. Velocity we can say 30 kilometers per hour. If we assume normal velocity nowadays here is 13 kilometers per hour, will give approximately 3.5 meters per second. I have taken 30 kilometers per hour as velocity, 30 kilometers per hour, that is 13 into 5 by 18. So that is approximately 3.5 meter per second. And the third one is 0.07. Now if I solve this, then I will be getting the value 0.15 plus 0.01 into 3.5 plus 0.192 air changes per hour. Okay. Now if I take a loose building, in loose building air changes per hour is going to be 0.25 plus 0.02 multiplied by 3.5, air velocity is 3.5 plus 0.022. Now if I solve this 0.25 plus 0.02 into 3.5, this is going to be 0.342 air changes per hour. Now you can see this is 0.342 and this is 0.192. The air changes per hour in the loose building is approximately 78 or 80% more. Now suppose I have a house of which is having a, the volume, inside volume, it is let us say house volume is 150 meter cube. It is not on very higher side. So air changes per hour is so suppose the building is loose, then 0.342. So 0.342 multiplied by 150 will give 51.3 meter cube per hour of air circulation in the house. Now 51.3 meter cube per hour is going to be I mean 51.3 into 1000, it will give liters divided by 3600. So 51.3 divided by 3.6, it is going to be 14.25 liters per second. So this is going to be the movement of air in the house. Now this infiltration in the house 14.25 liters per second. Now if the density of air I assume 1.2, if I assume 1.2, then 14.25 into 1.2, around 17 kg per second. It's very high. The velocity, this liters, no sorry, it is meter cube, 1.2 meter cube, sorry. It is 51.2, 51.3 multiplied by 1.2 divided by 3600, 260. It is 1 kg per minute, approximately 1 kg per minute. The infiltration in the house From here I will get this 51.3 meter cube per hour, or 51.3 into 1.2. I have considered the density of air divided by 60. This will give us kg per minute, and that is approximately 1 kg per minute. So that is quite considerable. So infiltration brings the load on the cooling coil. Infiltration brings the load on the cooling coil, and this causes unnecessary expenditure of energy in cooling the air. So, the infiltration is an undesired phenomena in a building, but it cannot be completely avoided, but it can be reduced to a certain extent so that the cooling load on the cooling coil is minimum. Now, in the next lecture, here I conclude this lecture. In the next lecture, we will take up the design conditions in the building. Thank you very much.